Hi everyone. Thank you for joining us on the second public session of the Embodied AI lecture series. Today, our guest is Shuran Song from Columbia University, and she's going to talk about self-adaptive manipulation. She's an assistant professor at Columbia University, and her research focuses on computer vision and robotics, and she has won many paper awards and Amazon Research Award and TRI Young Faculty Award, and recently she won the Transaction on Robotics Best Paper Award for the tossing bot. This time, we are going to have a bit of a different introduction. I was thinking maybe just asking Shuran a question Shuran, what is the project that you're the most excited about that is either ongoing or it's something that is recently finished?
That's actually a really hard question. It's very hard to pick like one project that I feel that's kind of shows very strong preferences. But maybe let me pick a direction. Yeah. So I think I think back then I work a lot on like how to make vision useful for manipulation or for robotics. But I think recently I'm more interested in how we can use like active agents that's able to build better perception system. So I think under that like big umbrella, there's a lot of work that I'm really excited about. Yeah, but I think that's like the general direction that I'm going for. Yeah.
Yeah. Thank you so much. So just a couple of communication rules. I'm going to initially mute everyone, but you can raise your hand if you have a question, and then I will unmute you. But please just mute your mic after you're done speaking. And at the end of the talk, we'll try to have a couple of minutes of open discussion. Yeah, and then that's it. With that being said, I am going to stop sharing, and Shuran, I'll let you take it from here.
Cool. So I probably will start sharing my screens. Video share. Okay. So are you guys able to see my screen?
Yes.
Okay, cool. Yeah. So hello everyone. I'm Shuran. Unfortunately, I'm not able. Hello, can you hear me now?
Yes, yes.
Okay, cool. Yeah, so unfortunately, I was not able to see you guys' face during my presentation, but if you have any question, just feel free to unmute yourself and ask me during the presentation. I also will remember to pause during the talk, and so that you guys can ask more questions. But I think at any point, just feel free to unmute yourself and ask questions. Okay, yeah, so today I'm going to talk about self-adaptive manipulation, where my goal is actually really just trying to use robot manipulation as an example in order to help us to kind of rethink about the role of robots' physical embodiments, and specifically in the context of embodied intelligence. Okay, so I think as today's audience, I'm pretty sure you guys are all very familiar with the field of artificial embodied intelligence, where the general goal is just try to develop embodied agents that are able to acquire intelligent behaviors through actively interacting with their environment. So under this big umbrella, I think people has worked on a lot of different applications and tasks, such as navigation, manipulation, and as well as some like high-level tasks such as question answering or object searching. So although all these applications and tasks, they are very different from each other in terms of the high-level goals, but they often share a very similar underlying problem formulation. So for example, typically the system will start with some kind of observations of the environment, often in the forms of images or videos. And then the goal of the agents is then try to infer what is the best next best action to take in order to accomplish the task. So for different tasks, the system will probably choose to use different type of action representation. So for example, for navigation, the agent will choose to use actions such as moving left or right. And for manipulation, the agent will choose actions from such as pick and place, right? So here in this formulation, the input to the system X typically represents the observation of the external environment. And the goal of the learning process is to acquire a suitable function F that would actually allow the agents to acquire a better understanding about the environment through active interaction. And as a result, hopefully in the end of the training, the system will be able to kind of generalize their knowledge to new environments or tasks. And as we see earlier, there has been a lot of recent works that show many promising results along this direction. However, there is one critical component in the system that has been overlooked in this problem formulation, which is the agent's physical embodiment. So in another word, the learned function F is often not aware of the physical embodiment of the agent, or at least does not explicitly model it. However, the actual physical embodiment or the robot's physical hardware is actually what really enables the system to be able to collect the visual observations of the environment and also the actual interface that allows them to perform actions or interact with the environment. So for example, in many of the embodied intelligent work, including many of my own, we try to abstract away the agent's physical embodiment by using like a heavily simplified or a fixed hardware model. So for example, in most of the simulation environments that we build for robot navigation, the agent's physical embodiment is typically represented by a very simple cylinder body and a camera on the top, right? So for many tasks like navigation, this kind of simplification is very reasonable and sometimes even necessary in order to make the task trackable for the system to learn. However, such a kind of simplification can quickly become unrealistic or inefficient for tasks that actually involves more complex physical interactions, which basically covers all the manipulation tasks. And also similarly, since the policy is trained with a fixed embodiment, the resulting model will often not work if part of the robot hardware is different or modified from the training setup. So for example, you can easily break a model or a learned model by just simply move the camera location or change the robot hardware to a different mobile manipulator. So in those cases, the system typically require a pretty extensive retraining or data on the data that's recollected on the new hardware platforms. So now let's take a step back and see why it is so important for the system to explicitly model its own physical hardwares, which I think can be generally summarized from two main aspects. So the first is that the agent's physical embodiment oftentimes actually directly defines agent's potential functionality and their performance by directly influencing the agent's possible sensor input and its available action space. So for example, where the camera is actually located on the robot will significantly influence on what kind of image or video observation the robot can obtain or capture about the environment. And similarly, the type of gripper or end effector the robot equips will also directly define what kind of objects that it can possibly pick up. So for example, if the robot only equipped with a parallel jaw gripper, then it is possible for the robot to pick up objects like potato or other like rigid objects. But it will be very challenging for such gripper to deal with granular media, such as pick up the right amount of salts or precisely manipulating different type of soups or liquids. Right. So, however, on the other hand, the target functionality of the system should also in return influence the agent's embodiment design. So in many cases, we can imagine that having the right type of physical embodiments or the right type of physical hardware could largely reduce the complexity of the task significantly, right? So if we go back to the earlier example of grippers, so if the goal of the robot is indeed try to handle different like granular media like salts or liquids like soup, then it will make the job a lot easier by just simply switching its end effector from a parallel jaw gripper to a spoon or similar shaped end effectors. So motivated by observations or examples like this, the goal of my today's talk is really try to put the agent's physical embodiment back to the equation. And then we'll focus our discussion on mostly on the applications in robot manipulation, which is typically the type of application that involves deeper dependencies between the learned policy and the robot's physical hardware. And that's lead to the main topics of my today's talk, self-adaptive manipulation. So the key idea for self-adaptive manipulation is to treat a robot's hardware as an integral part of its behavior instead of just a fixed parameter, which means that the learned manipulation policy should really be conditioned on the agent's hardware and also inform how the robot hardware should be improved in order to better adapt to the target task and environment. And concretely, I'm going to talk about two of our recent work to illustrate both ideas from like both aspects. Okay, so first let's look at how we can enable the robot to learn a manipulation policy that is aware of its own gripper hardware and and therefore able to infer different manipulation strategies for different available grippers. So in this project, we are looking at the task of object grasping, which is probably one of the most fundamental tasks in robotics or robot manipulation, and has been really well studied with many prior works in this area, right? However, as we described earlier before, most of these prior works actually use this like very incomplete problem formulation that considers only external environment as their input observation. So what they are trying to do is that taking image observation of the external environment, the system will try to infer how and where to grasp each individual objects. So under this formulation, typically the robot end effector hardware is considered as a fixed parameter in the system. However, as the actual physical interface between the robot and its environment, a robot's end effector or its gripper actually plays a very critical role in determining the system's functionality and performance. So as you can probably imagine, different gripper hardwares also requires quite different grasping strategies. And here is an example. So given the same environment or similar type of objects, a different gripper actually really need to choose different type of grasp poses in order to successfully grasp the objects and avoid collision. So for example, in this scene setup, the RG2 gripper, which has a much wider fixed opening, it needs to grasp the objects vertically in order to avoid colliding with other objects in the environment, such as the banana and also the triangle block. While the WSG50 gripper, which has a much smaller opening width, will choose to grasp the same objects with a horizontal grasp pose. On the other hand, the barrel-hand gripper will actually choose to grasp the bigger triangle shape, which is an object that is actually very challenging for the other two grippers, which only has 2 fingers. So in order to infer this kind of grasping strategies for different gripper, most of the existing grasping systems today will train a separate policy for each individual gripper hardware. So as a result, the learned policy will not be able to generalize to a novel gripper without extensive retraining or data collection. So our goal here is really try to learn a single policy that is able to produce different type of grasping strategies conditions on the input gripper geometry. And we call this algorithm AdaGrasp. So before we talk about how we're going to do it, I want to just highlight that this kind of capability would really benefit a robot manipulation system from multiple aspects. So first is that it actually provides the system a much better adaptability, which means that the system can quickly adapt to new gripper hardwares without the need of additional training data, or at least largely reduce the need for additional training data. And sometimes the new gripper can also be the existing gripper, however, it's damaged or broken, like missing one of the fingers. So in those cases, the capability of just quickly adjusting the grasping policy according to the hardware will allow the robot to continue its operation while waiting for the new hardware. So basically, it improves the resilience of the whole system. And the second advantage is actually such capability able to improve the system's versatility, which means that the system can now learn how to use a diverse set of manufactured tools. And since different gripper designs often provides complementary strengths and weaknesses, the system can now leverage a large variety of manufactured tools in order to handle a much bigger or larger variety of objects or tasks by automatically switching between different tools using an automatic tool changer. And here are examples of tool changers that people can use and actually is using in today's industry applications. And in order to allow the system to quickly switch between different tools automatically and efficiently. So in order to achieve this goal or this capability, we propose an algorithm called AdaGrasp. So the input to the algorithm is a 3D observation of the robot gripper and the environment. So the major difference is that we are no longer just input the observation of the environment, we also taking the gripper observation as the input to the system. And then the output of the algorithm is very similar to other grasping algorithm, which is basically the grasp score for all the candidate grasp poses. So here the grasp score is represented as a dense heat map where a higher score is encoded as red pixels and the lower score is encoded with blue pixels. And then in order to get these grasp scores for all the possible grasp locations, the algorithm will compute a very simple cross convolution between the gripper and the scene encoding. So this kind of cross convolution operation can be basically considered as a very efficient way of exhaustively matching the scene geometry with the input gripper geometry in all the possible grasp locations by translating the gripper kernel, where a good match will result in a higher grasp score. And in order to compute the grasp score for different orientations, the algorithm will then rotate the scene representation and then repeat earlier step. So the action, eventually, the action associated with the highest prediction score or the highest grasp score will be selected and executed by the system. And in order to further improve the grasp quality or the grasp success rate, the algorithm also has the option to compare and select between different input grippers with different initial configurations. So here, the different gripper initial configuration are basically treated as different grippers and then fit into the network in parallel. And eventually, the action that associates with the highest grasp score will be executed. So the action basically selects the grasp pose, initial configuration, and also the best gripper to execute. So here is an example results of like grasp proposals generated for two different grippers. So in this case, we have two grippers. One is RG2 gripper, the other is Barreham gripper. This two gripper has very different 3D geometry and also kinematic structures. One is 2-finger, the other is 3-finger. And in this example, we'll compare their grasp poses on the same object, which is a mag. Okay, so here is the predicted grasp score, where again, the red pixels indicate higher grasp score and the blue pixels indicate lower grasp score.
Just a quick question. So where does the model of the grasper come from? Is it from your own observation, or is it something that you get from the manufacturer or something?
Yeah, so I think this can be divided into two questions. So first is what's the input for the system. So for the algorithm, the input of the gripper is just a visual observation, which is like a 3D TSDF observation for the gripper. Like you just capture the depth image for the gripper. So basically, you just need to have the gripper in the real world. You capture the depth image and you reconstruct the 3D shape. And during training, because we build a simulation environment to train this kind of system, in the simulation environment, we use the CAD models that provided either by the manufacturer of who designed the gripper, or we manually kind of CAD out the gripper specifications and then use that for simulation.
Nice.
Mm-hmm. Any other questions?
So then during inference time for, I think you might mention this later, but when we go to objects that are novel and we haven't seen them, do you do this in real world and no simulation involved this time?
Yeah, so we during testing, later we'll show some results on real world. We basically just directly test the algorithms on unseen grippers and also unseen objects. And in those cases, the input is just the 3D TSDF volumes. We do not need the CAD models anymore.
And is this easily extendable to 3D? Because here, yeah, you have a planetary surface, and it's easy to do that, like 2D convolution and so on. But now imagine that you want to extend this to some kind of more realistic setting that objects can be in different heights and so on. So in that case, you have to exhaustively basically check all possible orientation of the gripper and do that in do the convolution in 3D space, and probably it's not as efficient anymore.
Yeah, exactly. I think so the type of task that we are considering here is basically like more specifically, it's like top-down grasp. So the grasp that we are predicting is only 4 degree of freedom. So it's like rotation and translation, and it is like a typical type of task that we consider in grasping. And I think what you're describing is this like full 6-stop grasp that's like really requires 3D position and also like 3D orientation as the final grasp pose. So and in order to extend this kind of work to 6-stop grasp is not that easy. And I think one of the biggest problem is the big action space. But we do have a few works that's trying to do this kind of extension using slightly different, but still like very similar type of idea of like try to infer this action affordance, but in a higher dimension through some kind of like more efficient samplings.
Thanks.
Mm-hmm. Yeah, so if you are interested, that work is called Grasping in the Wild, and it's specifically try to address the problem of like 6-stop grasp in the wild. Okay, so any other questions before I move on to the results? Okay, so let's take a look on this predicted grasp scores. So in this case, we can see that 2 different grippers, they will actually get pretty different grasp poses that's predicted by the network, right? So, oh yeah, so in order to understand this visualization, basically, apart from the red and blue pixels, you can also take a look on the white lines. That's basically indicating where the finger should be or what is the gripper orientation. And we can observe that for the RG2 gripper, which is on the top row, the algorithm really prefer to grasp the cap on the edge or the handle, which is those like smaller or thinner 3D structures on the cap. But on the other hand, for the 3-finger barrel hand, the algorithm will really prefer to grasp the object across the whole cap, since the gripper is much larger compared to the RG2 gripper. Yeah, so here is another example. So in this case, we actually have a target object that is surrounded by 2 obstacles. So here the target object is purple, and we on purpose just want the system to grasp the purple objects. And we will visualize the grasp score for the same gripper, but with slightly different initial configurations. So one of the configuration is only half open, means that it has a smaller gripper width, and the other one is fully opened, means that it has much bigger gripper width. And here is prediction results. We can see that the algorithm will choose to grasp vertically when the gripper has a smaller openings, since it's want to avoid because the object length is actually already longer than the gripper width. However, when the gripper has a larger width, it will try to grasp the object horizontally to avoid collisions with the other obstacles. So we can see that the algorithm indeed is able to kind of take into the gripper configuration into account and predict different grasp poses accordingly. And in the following experiments, we will compare our approach with another multi-gripper grasping algorithm, which is called UniGrasp. So the key idea for UniGrasp is to predict, to first predict potential contact points on the object surface based on the number of fingers of the input gripper. And then the algorithm will use inverse kinematics to compute the gripper joint configurations for grasp execution. So because the algorithm kind of need to rely on the contact point sampling, and the contact points is directly sampled on the object surface, the algorithm is actually, the algorithm UniGrasp is more sensitive to partial surface observations, since it cannot directly infer potential contact points on the surface that is not directly observed. So for example, in this case, we can see that the UniGrasp actually infers inaccurate contact points on the partial surface. Here are the blue dots. The blue dots basically visualize the contact points by the algorithm. So in contrast, and because it's kind of inaccurate contact point sampling, the algorithm is not able to correctly grasp the objects, but AdaGrasp is still able to reason about the object's grasp point beyond the visible surface by using a 3D volume representation. However, if we are able to increase the surface visibility with more cameras, then in this case, the UniGrasp will be able to correctly estimate a good contact point and able to successfully grasp the object. And apart from handling partial observations, AdaGrasp also has a clear advantage when handling cluttered environment with multiple objects. So in this case, even when we providing the complete surface as observation to UniGrasp, it will still fail to infer good grasp poses, since it will sample different contact points on different objects. And as a result, the system will not be able to grasp each individual objects. And here is another comparison for the cluttered environment. And here is some quantitative comparisons. On the left, we can see that when we decrease the scene observation with fewer and fewer cameras, the performance for UniGrasp will decrease quite significantly, while AdaGrasp is able to maintain a pretty constant performance throughout different visibilities. And on the other plots on the right, we can see that the AdaGrasp is able to kind of achieve much better performance when we consider cluttered environments with multiple objects. And here are more results in simulation where we are testing with novel objects, and we also test with novel grippers. So on the top row, we actually show the results for training grippers, and for the bottom row, we actually show the results for testing grippers that the system is not used or not seen during training. And you can also see that the algorithm is able to infer pretty different policies for different input grippers. And finally, we also validate our method on a real-world robot platform. So we used the UR5 robot arm with a single RGBD camera as the input observation. And the test objects, we used the objects from YCB dataset and the DexNet 2.0. So the testing gripper include RG2 gripper, WSG50 gripper, and also barrel hand gripper. we also include a variant of a barrel hand gripper with only 2 remaining fingers in order to mimic a damaged gripper hardware. So in this experiment, all the objects are unseen and also the grippers are unseen to the system.
Quick question, Shuran. If I understand correctly, the way you are formulating this model is a classification problem, right? So then this means that we are kind of implicitly inputting the kinematic constraint of the arms, even during the inference time, which is totally fine. But I was wondering if you tried anything that even the kinematic constraints of the arm, meaning that how much can I open the gripper, or what are the limits on the gripper, can be also taken into account and can be explored by the agent. Is this a topic that you explored?
Yeah, I think that's a very good question. So indeed, we so I think your if I reiterate your question is, do we consider for example, like the force limit or the kinematic limits of the end factor instead of just their 3D geometry? Is that correct? Yeah. So yes, indeed, we do not really consider those parameters, and I think that's one of the biggest limitations. So the system only considers the geometry, and the way that they consider the kinematics is by treating different initial configurations as a different gripper, basically, to evaluate the possible grasp scores. And the reason of that is that we want to use one policy to deal with all different grippers. But if we start to consider, for example, the joint parameters, then different gripper will have different number of joints, different number of actuators. Then as a result, the policy may need to infer different lengths of the output for the joint configurations. So that is a big challenge that we need to really address if we want to think about like more fine-grained controls on the joint level.
I see. Thank you.
Yeah, but that's something that we are indeed working on and thinking about. Yeah, I think that's a very good question. Okay, yeah, so this is the very simple results for single objects, and I think here is like more results for single objects. And here are some actually more interesting typical failure case for each individual grippers. So for example, when the object height is too small, the barrel hand gripper will actually has trouble grasping it. However, it is not a problem for the other 2 gripper. And on the other hand, for the objects like the big triangle block, it is actually very challenging for any of the 2-finger gripper to grasp it. But it was pretty straightforward for the 3-finger gripper because of its unique kinematics. So I think this kind of example really motivates that if the system is able to kind of leverage a diverse set of end factors, it will able to improve their overall performance. And here is more results on multiple object setting, which is like the cluttered environment. So you can see more details about this project's experiments, and the code is also available online in the project webpage. Okay, so to summarize, in this project, we basically studies how we can learn a unified grasping policy that is able to understand the input gripper hardware and infer different grasping policies accordingly. So as a result, the policy will be able to generalize to new gripper designs without additional training. So before I move on, is there any questions about this project? Okay, so in the next project, we want to see that apart from adapting the software policy for different gripper hardware, we want to show kind of in the other way around, is that possible for a robot to directly change or optimize their own hardware, gripper hardware design in order to improve their performance for the target task. For this project, the title is called Fit to Form, where our goal is try to develop a 3D generative model for a robot gripper form design or shape design. And then before I talk about our message, I just want to kind of quickly point out that in nature, it is actually very common for animals to evolve and develop all kinds of specialized embodiments as a way to help them better adapt to the specific living environment or habitat. So here is a famous examples of Darwin's finches. So among all different species, like within the finches, the ground finches actually developed a much wider and shorter beaks that are particularly good for cracking nuts. And on the other hand, the cactus finches has long and curvy beaks that is evolved for probing flowers. So it is really interesting to see what the beaks are basically just like tools for the birds, where different shapes are optimized for different jobs. So the question here is, can we allow our robots to do the same, basically evolve their own hardware in order to better adapt to different jobs? So in fact, in most of the industry automation systems today that is actually used for manufacturing, for example, they are all using very highly customized end effector designs or grippers for their target task. And compared to the general purpose grippers that we are typically used in research, like the parallel jaw grippers, this kind of specialized grippers can actually significantly improve the system's overall performance and robustness in a lot of practical applications. And in many cases, this kind of specialized gripper can also simplify the overall system. You can basically imagine that with kind of special gripper design, the policy can be much more simplified compared to like general purpose grippers. However, the downside is that manually designing all these grippers actually requires a lot of engineering experience and trial and error testing, which are quite costly and time consuming. So the question we have here is that, can we use machine learning algorithm to automate this kind of design process and then generate task-specific gripper designs efficiently? So in this project, we studied the problem of end effector shape design. So basically, we formulate our problem as following. So given a target object that described by their 3D geometry, the goal of the algorithm is to generate a pair of 3D finger shapes for a parallel jaw gripper that would maximize the several design objectives. So first is that the gripper should be able to successfully grasp the object, which is quite important, like the grasp success. And the second is that even after the gripper is able to grasp the object, it should also be able to maintain the grasp under external forces, which we call grasp stability. And the third is that the gripper should also be able to grasp the target objects with perturbations in their orientation. And we call this property as grasp robustness. Means that even if the object's poses is shifted like 10 degree, 20 degree, the gripper should still be able to grasp them. So that's called robustness. And in addition to those design objectives, the generated finger should also be feasible to manufacture, right? In our case, we are going to 3D print those generated fingers. Therefore, we need to make sure that the generated shapes are 3D printable. So specifically, we need to make sure that the generated shape will be connected to base. And also, the generated finger shapes should only contain a single connected component. Otherwise, it will not be able to like really 3D print it by the 3D printers, which is just not physically possible. So as a result, the feasibility test is basically we want the just generated finger shape is a single connected component and connected to base. So, okay, so now we are clear about the task objective. The next step is to figure out what is the approach that we can allow us to achieve this goal.
That's a quick question, Sure. So in simulation, yeah, we can generate like new grippers and so on. But what is the equivalent in the real world? I mean, how is that going to be implemented in the real world? Is it just the robot? Is it just the change of the shape of the gripper? How does that happen?
Yeah, so I will actually show you some of the real world implementation of this gripper design. So maybe like spoilers. So basically, because we formulate our problem in this way, we do not change the kinematic structure of the gripper. So we still assume it's a paralogical gripper, but it can change the finger shape. So what we do is that we have an existing gripper, which is a WH350 gripper, and then we will basically unmount the original finger, and then we put back the newly generated gripper from the algorithm, and then we can test the performance of those grippers in real world.
Okay.
Yeah, so actually those kind of gripper like WH350 or a lot of industrial gripper, they are designed in a way that is modularized so that you can swap out the finger shapes quickly and easily for different tasks. And that's what we leverage to do our real world experiment.
Okay.
Okay, yeah, so back to the algorithm. So there are actually basically two main challenges in order for us to really accomplish this goal or finish this task. So first is how we can kind of represent this collection of high-level design objectives that we just described earlier, so basically in a differentiable manner so that we can allow the efficient learning, right? So we want to formulate this problem as a learning problem, and therefore we need to kind of also formulate our design objectives in a way that is differentiable and therefore can provide gradients for the generation model. And the second,
hello, I had a question. So are you also assuming that your the two hands would be symmetrical?
yeah, so that's another, we do not assume that the two fingers will be symmetrical. And later you'll see that the algorithm actually do not generate symmetrical grippers at all. So they actually choose different designs for different fingers.
I see. And one more question is, for robustness, you chose rotation, right? Like you 10-degree, it might be off. So also, are you assuming for translation, like it's not exactly, the center is not at the coordinate, it's shifted by some.
Yeah, so I think I'm not exactly remember whether I think that we also evaluate translation in our paper, at least in supplemental material. It's basically can be formulated in a similar way, but I think during training we only train for rotation robustness, which is typically harder to handle than translation. Basically, because it's a paralogical gripper, you can imagine that the translation on the X dimension, it doesn't really matter that much. So
yeah,
rotation
so basically, if you had translation plus rotation, would it become more complicated, or would it be very similar to what you are already assuming?
Yeah, I think the problem will definitely be much more complicated. But if I remember it correctly, once the model trained with the rotation robustness, it's also it's able to handle to a certain degree about the translation variance.
Thank you.
Yeah. Any other questions? Okay. Okay, so the second challenge, which is how we can efficiently navigate such a large design space in order to produce a feasible solution. So basically in this project, we do not like parameterize our design space into like certain primitives, but instead we allow the system to generate all possible shapes, that's whatever shapes that can be described by a 30 by 30 by 30 cube volume. So if you think about it, it's really a large design space that the system needs to kind of navigate and explore in order to generate feasible solutions. So finding a good way to model the design objectives and finding a good way to navigate the design space is the two major challenge for this for this task. And here is our solution. So first, in order to effectively model the design objective, we train a fitness network that's explicitly trained to predict the values of each of the design objectives for a given pair of gripper fingers and also the target object. So basically, this fitness network combines all the high-level design objectives that we want, such as grasp success, stability, and robustness, into a single learnable objective function. And this function is learned from grasping data with different gripper shapes and target objects in simulation. And since it's modeled by a neural network, it is fully differentiable and therefore able to provide meaningful guidance on the gripper generation. And then in order to efficiently navigate the large design space, we use a 3D generator network that try to model the general distributions of 3D shapes and then produce the 3D fingers geometries based on the target object, grasp objects. So basically this generator network taking the target objects as input and then produce two shapes as the left and right finger shapes. And the parameters for the generator network can be directly optimized to maximize the fitness network's output score. So basically, what's the supervision we use for the generator network is the output of the fitness network. What we want is the generator network that's able to generate shapes that maximize the fitness score. So that's the overall learning pipeline setup. And during training, both the generator network's parameter and the fitness network parameters optimize jointly. Any questions? Okay, so that is the learning frameworks, how we set up the learning.
I have a question. So how do you quantify stability and robustness?
Yeah, so stability is whether after you grasp the objects, if you are able to successfully grasp objects, the object will still be grasped if you apply external forces. So how we actually implement it is we will apply external forces from several different dimensions. I don't remember exactly how many, but like imagine 5, for example. And then each of the force will have an outcome. Basically, it's a binary 0 and 1. One means that it's stable. And
who applies those forces?
It's in simulation. So in the during training, we'll apply the virtual forces in simulation. Okay. And similarly for robustness, basically we'll just reset the object pose with different orientations and ask the system to grasp the object. And then again, the outcome is labeled as binary. 0 is failure, 1 is successful. Okay, so we have the networks, and now we just need to think about how to train it, right? So one of the critical challenge for training these two networks together is how to get the initial positive training data, right? So as you can imagine, the shape generated by the generator network is very likely to be invalid in the beginning of the training. It can generate any type of shapes, and most of the time it will not be a good gripper. So without any, however, on the other hand, without any good examples of like what is a valid gripper, the fitness network will not be able to learn a very reasonable evaluation function, right? So for the fitness network, it cannot need to see relatively balanced positive and negative examples. So one possible solution is that we can use those existing manually designed grippers as positive example to train the fitness network. However, since that we have very limited number of manually designed gripper, in this case, for this gripper, we only have one manually designed gripper, finger shapes. So it is really not sufficient to train the fitness network in order for it to learn a general distribution over diverse gripper shapes. So in order to address this issue, we actually use a trick or hack in the early stage of the training. Basically, we'll randomly sample shapes from the shape data set and then use them as fingers to test the grasp performance. So here on the slides, you can basically see we sample different like chairs and tables, and we just use those shapes as fingers directly. And then we can test their grasp scores or stability or robustness with respect to different objects. So this data set actually provides us a very diverse training set that contains both positive and negative examples. So as you can imagine, it probably has more negative examples, but we can like sample it so that we have a balanced set. And with this kind of data set, we can initialize the training for the fitness network and the generator network. Okay, so here are some like example designs that's generated by our algorithm, and we 3D print those designs and we mount it on the WSG50 grippers. As you can see, the white part is the 3D printed fingers, and the base is the same parallel jaw gripper base. And then we can replace those fingers with the generated fingers and also 3D printed. And the target objects that we used to test our algorithm is called adversary grasp objects, proposed by Ken Gober's group in Berkeley, where those objects are actually intrinsically designed to be hard to grasp by a typical parallel jaw gripper. And in our experiments, we mostly compare against two major baselines. So one is the original WSG50 gripper, and to make the comparison, focus on the finger geometry inside the material. We basically 3D print original gripper with the same material as ours. And the other baseline that we compared against is so-called Imprint gripper, where the gripper basically produces the inverted geometry compared to the target objects. So this kind of Imprint gripper, as you can imagine, is quite powerful, and it's also very popular method in industry applications for generating object-specific grippers. However, we'll see in the later experiments is that this kind of designs generated by the Imprint algorithm often requires a lot of careful manual tuning in order for them to work properly, especially when the target object has complicated 3D geometries. And more importantly, this kind of gripper are very sensitive to the object post-estimation accuracy, which means that a small misalignment will result in failure grasps. So in other words, the robust score is typically much lower for this kind of Imprint grippers. So here is the grasp experiment. So we first compare the grasp success, and on the bottom of each of the video, you can actually see the labeled results. So now it's the stability, and then in the end, we'll test the robustness. And quantitatively, our algorithm is also able to generate gripper designs that achieve more stable and robust grasps compared to alternative approach. And so here is just like a plot to show the different metrics, and our method is able to kind of produce a better performance compared to other baselines and also alternative like application studies that we did in our paper. But I think a more interesting question that's I'd like to think about here is actually what kind of general strategies can or did the algorithm learn in order to optimize its gripper designs for the task? Does the algorithm actually learn some strategy that is smart or non-trivial, right? So motivated by this kind of question, we really want to take a closer and careful look on the generated grippers, and then just to see what kind of general strategies does it learn. So here I'm going to show you a few examples of like the typical strategies that we kind of summarized by looking at overall the generated fingers or like the results. So the first and maybe the most common strategy that we found amongst all generated gripper is what we call single-sided scoop. So like this also kind of answers the earlier question is whether the system will generate symmetrical fingers. The answer is no, and in this case, they actually generate very different fingers for each side. So on one side, the algorithm will generate a finger that is hollow in the middle, and on the other side is actually have a very flat surface. And then during grasping, what will happen is that the flat surface will actually push the object inside the cavity of the other finger in order to successfully grasp the object. And on the right, we also show the comparisons with the baseline algorithms of using Imprint gripper. So surprisingly, this simple strategy is used very frequently by the algorithm. And another related strategy that we found is called double-sided scoop, which is very similar to the single-sided scoop, but for much larger objects. So in this case, both fingers will have a significant amount of empty space in order to cage larger objects. And we can also find that the algorithm will try to generate those kind of protruding structures on the side in order to improve the stability of the grasp. And on the right is again the Imprint gripper for comparison. And another common strategy that the system used or the algorithm learned is quite different from the earlier two caging behavior, where the key feature is that instead of directly generating or creating a form closure around the object, the algorithm will actually generate a finger shape that has some special geometries, protruding geometries that is able to hook the target object during the lifting process. And here is the example, right? So it's no longer just completely enclosing the whole object, but instead it's trying to hook up the object during the lifting process. And we call this strategy dynamic hook. So in this case, actually the imprint gripper will actually not able to pick up this object without this kind of strategy. And then lastly, for the objects with a lot of detailed geometries, the imprint gripper actually are very sensitive to any small misalignments. So here is an examples of like a chair that's with very detailed or complicated 3D geometry. Any small misalignment will make the imprint gripper fail. So in this case, the fit-to-form algorithm will able to relax the shape and then generate a finger that is able to, again, form a closure around the object and also have some extra space in order for better robustness. So to summarize, in this project, we introduced a 3D generative design framework that used machine learning algorithm to automate the process of robot gripper hardware design. And specifically, we focus on the gripper design instead of the whole robot hardware design. So the experiment shows that it is possible to generate gripper shape sets for a target object that are able to achieve more stable and robust grasps. So the code and data for both of the projects are already available on the project webpage. So if you want to know more about either of the projects, you can just go ahead and check it out. I think the code, data, everything is there. And however, we are obviously not really done here. So I want to kind of just provide some thoughts or ideas about what's the potential next steps or future works along this direction. So as you can probably tell, that in both of the projects that I talked about today, we only covers a very tiny part of the robot's whole embodiment, which is only the robot's end effector. So although we can argue that it is one of the most important part of the embodiment, it is obviously not the only part that matters, right? So for example, the robot's arm structure and its mobile base can also directly influence the robot's potential action space in the environment, and therefore has a strong impact on the robot's performance and functionality. And therefore, we really should consider the agent's whole body motion planning in our problem formulation as the next step. And another important component in the agent's embodiment is their sensor input hardwares, including both the sensory modalities and also their physical placement. So for both projects I present today, we only consider one type of input, which is visual data, more specifically like RGBD or 3D depth visual input. However, on a real robot platform, we can collect many possible sensory inputs, such as tactile sensors, force torque sensors, or even sound inputs. And knowing when and how to use different kind of sensory inputs is a critical skill for almost any embodied intelligence system. And we have not yet discussed, or I have not yet worked on it. And also, even if we only consider one type of input, which is a visual input, the placement of the sensor, where to place the camera, can be also be a very important task, or could be optimized for the final target functionality of the task. And here again is an example from nature, where different animals actually frequently, not frequently, but they often optimize their eye locations according to their functionality or their role in the environment. So for example, the predators often has a much larger view intersections just for better stereo vision, which is critical for estimating accurate 3D spatial information. However, on the other hand, prey typically has a much wider overall field of view in order for detecting potential threats in the environment. So it will be interesting to just think about whether we can allow our robots or our agents also learn where a better camera placement or where I should place my sensor in order for to better handle different tasks, right? So for example, the camera placement for object searching or in-hand manipulation may be very different, may have very different requirements, and therefore they require different camera placement. And lastly, even if we just consider the robot end effectors, there is still a lot more parameters or aspects about gripper or the end effector the algorithm should take into account, but not yet. when inferring the corresponding grasping policy. Right. So for example, our current algorithm mostly focuses on understanding and optimizing the 3D shape of the gripper, which is the 3D geometry. They do not explicitly reason about other physical properties, such as their deformation, friction, or contact mechanisms, which are all the necessary information to consider when the system is dealing with more complex end effectors, such as deformable gripper or suction-based grippers. So yeah, to summarize, as you can tell, there's still a long way to go for us to really achieve embodied intelligence. And while we are all moving towards it, I think it is very important to keep in mind that the ultimate goal is not just about designing different softwares on a fixed or predefined robot hardware, but instead we should treat the agent's physical embodiments as an integral part of its behavior. And I hope that by reconnecting the system's hardware and also their software optimization, we can observe better synergies between these two components, and therefore really develop the system that is able to adapt to the environment changes, resilient to potential hardware damages, and also be versatile in handling a wide variety of tasks. Yeah, so I think, yeah, that's the end of my talk. And I want to thank all my students who actually make all the work possible, and also the funding agencies, and I'm happy to take questions.
Very interesting talk, Shuran. This actually reminded me of two work that I think it's very interesting if you haven't seen them already. One of them is from David Ha, Reinforcement Learning for Improving Agent Design, where they're focused on how the embodiment should change as they put agents in the humanoid agents for like walking in different environments. Another one is Malcolm's work. He gave a talk. His talk is on our YouTube channel, and their observation was that during the evolutionary process of animals coming into land, their behavior and their body parts actually changed. So this is, I think, very aligned with what you just mentioned. So if you haven't checked them out, I think those works are also very interesting. Thank you for the talk.
Thank you.
Do we have any other questions?
Just a quick comment. I mean, about the second part of the talk. It would be more interesting if that manual process was not part of was not in the loop, like getting the model, like 3D print that gripper and then install it on the robot. That's something. It would be even more interesting if that happened automatically on the real robot, like shape changes or something happens.
Yeah, I think that's a really cool idea, and I also feel like we are very close to get there, right? So basically, the 3D design is automatic, and 3D printing is just sending the file to the 3D printer, and then putting the gripper, putting the finger onto the gripper is actually an assembly task that we worked on before. Yeah. So yeah, I guess it's possible, and I think it's really, really cool if the whole thing is just the robot actually generating itself and work out from the 3D printer.
Yeah. And one more comment. So have you tried this on unseen objects? So I guess the same objects are used for training and testing. So have you tried it on unseen objects? For example, you have a set of like generated grippers, like which one fits better? Is a better fit for the object that they've not seen before?
Yeah, so I think for both projects, actually, they were tested on unseen objects. So for the gripper generative part, is once we train a lot of different shapes and different target objects, but once we trained it during testing, we can give them a new shape. And then the generator will actually generate new designs based on, like, the weight of the generator actually do not need to update it. It will generate new fingers. And I think for the first project also, like given a new, we are tested on novel objects and also novel grippers. So actually the system needs to just look at what are existing grippers that are available, and I can choose which gripper is more suitable for the target object.
I see.
I guess I was just going to take Rizba's first question one step further. Have you thought about, replacing the 3D printed step with some sort of deformable surface on the gripper that could, really respond dynamically to a new object?
Yeah, I think that's really cool, and I really want to get there, but I have no expertise in material science. So if you have any good idea, like what's good material we can use that can easily deform to a target shape, or like, yeah, let me know. I'm very interested in that.
There are some cool systems. I don't know if they're light enough and small enough to sort of deploy on the end of a robot arm yet, but yeah, they do exist. But yeah, I'll try to find some.
Cool.
Okay, awesome. Thank you so much, Shuran. This was an amazing talk, and it was great having you here at AI2. Hope to see you soon again. Yeah. Thank you all for joining. Bye.
Bye-bye.